Hello and welcome to 10-Minute Physics. In this video, in 10 minutes or less, we shall take a look at the law of conservation of momentum. Before we do, I want to just remind us of Newton's third law. And we had said last time that the force exerted by object A on object B was going to be equal and opposite to the force exerted by object B on object A. Now, I just wanted to talk really quickly about this this negative sign here. Okay, if you take a look at another equation that we have, if you get one of these questions where I don't know, we've got a little container full of water, we heat up some big chunk of iron, a block of iron, and we put it in there, and what will the temperature change of the water be? Well, in those equations, we usually talk about the heat gained by the cube being equal to the heat lost by the water. Okay, now what ends up happening, because these equations involve a change in temperature where you have final temperature minus the initial temperature, what happens is that this heat lost is intrinsically a negative value, because the higher temperature of this metal to begin with is going to be subtracted from a final temperature which will be lower. So this is intrinsically negative. In order to make these things actually equal, because if you were to put in your formula there with your delta T, this delta T will be negative. So what is often done is they put a negative sign out front here, because once you get the negative T's involved, if I say 3 is equal to negative 3, that would be wrong. Right? But what happens is, by having an explicit negative out front here, okay, now I can say negative minus 3, and I can say 3 is equal to 3. And there I can say, in terms of heat loss and heat gain, they are equal. If you look vectorially at what's going on with these forces, it's kind of the same thing there. That's why we have a negative. Okay, vectorially, this value is intrinsically negative. You put a negative in front out, and a negative, of course, is a positive, and both of these magnitudes will be vectorially equal. Okay. Anyway, let's get on with this now. Okay. So from Newton's third law, this is what we had said last time. This is what we just talked about a moment ago. Okay. If you were to multiply both sides of this equation by a certain time interval and have these forces exerted for a certain amount of time, now we've got some impulses, don't we? Okay. And these impulses will be equal and in opposite directions. Okay, and what that should mean then is that the force of A acting on B is going to result in a change in momentum for B, and this force of B acting on A will result in a change in momentum of object A. And so you can see here this equates to having a change in momentum of object B equal and opposite to a change in momentum of object A. Okay. Now, if we were to expand out what this delta PB and delta PA mean, it means that we're going to have the final momentum minus the initial momentum. Okay. And of course, I'm using a little prime symbol here for this is the final momentum of B minus the initial momentum of B. We have the same thing here, except this is a negative sign. So if I take that negative out front, okay, and have a bracket, and then I multiply that bracket through, what I'm going to have is I'm going to have negative the final momentum of A. Okay, I'm going to subtract, but I'm going to multiply a negative to the initial momentum of A. Okay, so what that means is I'm going to have a plus initial momentum of the A, and I'm going to bring this negative over. This is the momentum of B. This is the initial momentum on the right side. And on the left side, I have the sum of the final momenta. This negative P primed A is going to move over to the left side. And you can see here, so what we are saying is the final momenta, which is plural momentum, is equal to the initial momenta for these two objects. And this is called the law of conservation of momentum. It is a direct result of Newton's third law. Okay. Another way we could have written this, we could have just kept this minus delta PA sub A, and we could have brought it over to the left side and just said, look, the change in momentum of object A plus the change in momentum of object B is equal to 0. So this is what we mean by conservation. Okay, the change is 0. In other words, there is no change. The total momenta is constant. Now, you might see that as a sigma or sum of all the forces added together equaling 0. Okay, if we add them all up, they've equaled 0. There is no net force. These forces are balanced. Now, this is crucial for our law of conservation of momentum, okay, or our theorem. Okay, in a closed system, one that does not exchange any matter with its surroundings and is not acted upon by external forces, the total momentum is constant. And this is where most students get this wrong. This is where most students have mistakes in understanding. Okay, we can't just say momentum is always constant. Momentum is always conserved. So here's the thing. The total momentum is constant, but that's in a closed system. Usually in your GCSE and in your A-level exams, you'll have these questions, and it'll be 2 marks, and you need to say the closed system, and that typically we say not acted upon by external forces. There is no net external unbalanced force. Why? Well, this whole expression that we started off with came from up above when we were talking about Newton's third law, where force of A on B is equal opposite to force of B on A. So that right there, if we were to bring this force over to the opposite side, then we'd have FAB plus FBA equaling 0, meaning there is no net force. So because this law derives from Newton's third law, and Newton's third law says the forces are equal, if the forces are equal, they are balanced, there is no net force, Newton's first law. Okay, so this whole conservation of momentum relies on the fact that we have no external forces. Okay, also keep in mind we are not exchanging any matter with the surroundings. That means mass is constant as well. Okay, because momentum is mass times velocity. So if you've got material flaking off of an object as it's traveling through the air, if you've got a plane traveling along and it's building up ice on the wings because it's in a polar storm, if you're changing the mass of something, you will be changing its momentum. Okay, and so we are assuming there's been no change in matter, no change in mass. The mass is constant, and therefore the forces acting upon them are also constant. Okay, this is very crucial. This is what you must remember. This is your typical definition. 1 mark in a closed system usually will get you 1 mark. The total momentum is constant. You could say the total momentum of a system, okay, but the total momentum of these objects you're talking about should be constant if it's been conserved. This will work for single objects or many particles in any reference frame, okay? And this is why we have things like recoil. When you fire a rifle, the bullet is exerted forward. It has a small mass, high velocity, but that rifle with a higher mass will still have a low velocity. Some people get injured because they don't expect that much of a kick. Okay, these types of things, explosions and recoil and rockets, that's where we have the initial momentum starting as 0 and the final momentum being in 2 different directions. Now, if you take a look at this, if you've got 2 vectors being added together where they're equal to 0, one of those numbers, actually they don't even need to be vectors really, but one of those numbers needs to be negative, don't they? Because a positive plus a negative will give you 0. We can also have an object, coming to rest, change in momentum. So you can talk about seatbelts and crumple zones. You can talk about billiard balls, cars hitting, that sort of thing. Okay, but this whole thing comes from the fact that we are saying in a closed system, 1 mark, total momentum is constant. Why? Because it's derived right from Newton's third law. Okay, great. All right, that takes us to the end. If you've got any comments, questions, please leave them down below. If you've got any requests, please let me know as well. Comment, rate, and share the video. Thank you very much. We'll see you next time on 10-Minute Physics.